You know, almost every single electronic gadget you own, from your phone to your smart toaster, is governed by a set of invisible rules. In this explainer, we're going to pull back the curtain on the FCC's Part 15 regulations. These are the crucial rules that stop our super-connected digital world from just dissolving into electronic chaos.
You've definitely been there, right? Or maybe your car radio gets all staticky when you drive under some heavy power lines. Well, that annoying crackle, that static, that is electronic interference. It's not some ghost in the machine. It's the very problem these rules were created to solve.
The solution to this problem is a concept called electromagnetic compatibility, or EMC for short. The easiest way to think about it is being a good electronic citizen. See, EMC has two sides. First, your device has to be tough enough to handle a certain amount of electronic noise from everything around it. We call that immunity. And second, your device can't create so much noise that it starts bothering other devices, and that's called emissions.
So who sets the rules for this electronic neighborhood? Well, in the United States, that job belongs to the Federal Communications Commission. You know them as the FCC. They are the gatekeepers, the referees, making sure the symphony of all our devices doesn't just turn into a noisy mess of interference.
So here's the game plan for today. We'll quickly touch on the noise problem, then dive deep into the FCC's main rulebook, Part 15. We'll figure out the really important difference between Class A and Class B devices, walk through the main tests they have to pass, and finally, look at what else it takes to get a product on the shelf.
All right, let's get into it. Our main focus is Part 15, Subpart B of the FCC rules. Now this is the big one. It covers what the FCC calls unintentional radiators, which is a technical-sounding name for basically any device that gives off radio frequency energy just by doing its job. And you might be asking, what exactly is a digital device to the FCC? Well, the definition is huge, and that's on purpose. If it uses digital circuits and has a clock speed faster than 9 kilohertz, just 9,000 cycles per second, it's covered. That means your laptop, your digital watch, even your fancy new coffee maker. Pretty much anything with a chip in it falls right under this umbrella. Okay, so once a product is identified as a digital device, it has to go down one of two paths. This is the first and maybe the most crucial fork in the road for any company making electronics. And it all comes down to a really simple question. Where is this product going to be used?
So, the two paths are Class A, which is for commercial or industrial settings, and Class B, which is for the home. So what's the big difference? Well, a Class B device, like your TV or your Wi-Fi router, is probably sitting right next to a radio or another sensitive device. Because of that, its noise limits are about 10 decibels stricter. Now, 10 dB might not sound like much, but in the world of engineering, it means the device has to be 10 times quieter. That is a massive, massive challenge for designers.
So how does a product actually prove it's a good electronic citizen? Well, it has to pass two big emission tests. These tests measure all the unwanted electronic noise it's putting out into the world.
The first trial is for radiated emissions. This is noise that literally escapes the device and travels through the air as radio waves. The analogy here is just perfect. It's like a device that's playing music way too loud in a quiet neighborhood, and it could disrupt everybody else around it. And this picture shows you exactly how they measure that noise. This is a standard open area test site, or OATS. The device being tested, which they call the EUT, sits on that turntable. And a special antenna, placed a few meters away, listens very, very carefully for any stray radio noise. They rotate the device, move the antenna up and down, all to find the absolute worst-case, loudest emission it can possibly make. Now take a look at this table. It shows you just how strict those limits are for a Class B home device. The allowed field strength is measured in microvolts per meter. That's millions of a volt. It is an incredibly small amount of energy. To give you some perspective, the faintest radio stations you can barely tune into are often stronger than these legal limits. Hitting these numbers is a serious piece of engineering. Okay, so that was noise going through the air. The second test is for conducted emissions. This is noise that doesn't fly through the air, but instead it travels back through the power cord and pollutes the entire AC power grid. The analogy of polluting a shared water supply is just perfect. That noise can then travel into your neighbor's house and mess with their electronics.
And here are the limits for that. You'll notice there are two different types of measurements here. Quasi-peak is a special detector that's really good at catching those sharp, brief spikes of noise. You know, like the little tick from a digital clock circuit. Average, on the other hand, measures the more constant, humming background noise. A device has to stay below both of these lines to pass. Whew. Okay, that was a lot of technical detail, I know. But hey, if you're finding these kinds of engineering deep dives helpful, please just take a second to hit the like button, share this with someone who might find it interesting, and subscribe to our YouTube channel, Spectrum Speak. It honestly helps us out a ton.
All right, so let's say a product passes both of those big emission tests. It's home free, right? Well, not quite. Passing the tests is the biggest part of the battle, sure, but it's not the whole war. There's more to it.
You've got the whole administrative side of things, which is just as important. I'm talking about the paperwork. The product has to have the correct FCC label on it so you know it's approved. The user manual has to have specific warnings about interference. And here's the big one. The responsibility doesn't just end after one unit passes. The manufacturer has to make sure every single unit that rolls off the assembly line is still compliant. If they change anything, even something as simple as moving a wire, they might have to do the entire test all over again. Now, remember when we started, we talked about two sides of EMC? We've been focused on how much noise a device makes. But what about how much noise it can take? That's called susceptibility, or immunity. And what's interesting is that in the US, the FCC doesn't really enforce immunity rules for most consumer products. It's more of an honor system. But it's still so important because nobody wants a product that just stops working every time a cell phone rings nearby.
It's also really important to know that these FCC rules are just the baseline. Some industries are playing in a whole different league. Medical equipment, big telecom gear, and especially automotive electronics, they all have their own much tougher rules for both emissions and immunity. I mean, it makes sense, right? The consequences of failure in a car or a hospital are just too high.
And this really brings us to the core idea, which is summed up perfectly in this quote from an EMC engineering legend, Henry W. Ott. He said, "Electromagnetic compatibility should be a major design objective." In other words, you can't just build something and then try to sprinkle some magic EMC fixing dust on it at the end. It has to be baked into the design from the very first sketch.
So, what's the big takeaway from all of this? It's simple, really. Complying with FCC Part 15 isn't just a sign of good engineering, and it's not an optional add-on. It's the law. It is the non-negotiable ticket to entry if you want to sell an electronic product in the US. It's what keeps all of our amazing gadgets living together in peace.
And that leaves me with one final question for you to think about. In our world of the Internet of Things, 5G, and a future that's going to have trillions of connected devices, the world is getting electronically noisier every single second. How will these foundational rules we've talked about today have to change and adapt to keep everything working and to prevent total electronic chaos? Thanks for joining me.